What I want to talk about today as our first revision lesson is actually something we didn't cover, and that is parametric integration. So we've looked at functions where the x and the y part of a coordinate are defined separately. They're called parametric equations. And we looked at turning them to Cartesian equations, and we've looked at differentiating them. Differentiating them is specifically mentioned on the pre-release. Doesn't mean that the Cartesian conversion won't come up, but differentiation is specifically mentioned on the pre-release. But what we didn't do is integrate. And so that's what I want to talk about. Before we do that, I just want you to do a couple of basic integration for me. So I'd like you firstly to integrate that. And that's easy because it's two things divided by one thing. You can split that up into two separate fractions. I'd then like you to integrate that, and there's a couple of ways we could do that, but I'd like you to use substitution. Okay, so just have a go at those two integrations. The one on the left is easy because two things divided by one thing, I can split it into two separate fractions, and it gives me things that I can easily integrate. But the one on the right, you can't split one thing over two things into two separate fractions. We've got a couple of techniques we could use, but I'm suggesting you use the substitution u equals x plus 1. So that's just revising the whole integration by substitution thing.
You want us to do that now?
Yes, both of those, yeah. Remember, when you integrate by substitution, you need to replace the dx with du. So you need to differentiate your substitution statement and rearrange it to get a dx equals statement.
Still recording.
I am, yeah. Don't be shy.
It's my first appearance on the channel.
So on the left-hand side, I just get 1 plus 1 over x. I can integrate 1 when x is the variable. I just get x, and 1 over x is the ln of x. So when we're integrating any 1 over statement, we must remember the modulus signs there, just so we don't fall foul of any trying to log negative problems. Oh, George. On the right-hand side, so you know, I have my, I call it my little scratch pad, don't I? So I've sort of got all my little work going on here. I needed an expression for x, so I just rearranged it to get x is u minus 1. I needed to replace dx with du, so I differentiated this. Du by dx is just 1, and that rearranges really nicely. Multiply both sides by dx, so I can just do a straight swap in that case. So this becomes this, which is 2 things divided by 1 thing. So now I can split it up. And I can integrate that because that becomes u, remember u is my variable, minus the ln of u plus c. And because the original question was in terms of x, I'm going to replace u with x plus 1. Of course, if I had been asked to do an integration between 2 values, I wouldn't have had to do that step at the end, because I would have changed my x values into u values, and I would have substituted them in at that point to get the actual area that I was after. This wasn't the area question, this was an indefinite integral. Yeah, sorry.
Why is it that we need to put the in modular sign?
We can't log a negative number. So the graph of ln of x looks like this. So you can't log a negative number, so we need to make sure that when we're substituting values in, we don't fall foul of that. Right. And you know, I make no apology for the fact that over the next 4 and a bit weeks, we're going to be regularly, you know, reminding you about these sorts of things. So we've already reminded you about differentiating tree, integrating 1 over x, integration by substitution. So let's now come to what this lesson is about. So we are asked to integrate that function between 2 and 14. But that function is not given to us as a y equals statement. It is given to us in parametric form. So we need to integrate it, but we need a technique for doing it. And the good news is, it's a really simple technique. So I want to integrate this y equals function. Well, I've got an expression for y. Y is t squared minus 9t plus 20. So I've got my y equals expression from the parametric thing there. However, the problem is that I've got dx there, and this has got t as the variable. But I can solve that problem because I've used the y equals part of the parametric function. I'm now going to use the x equals, but I'm not going to just whack it in there. I'm going to separately say, right, if x is equal to t squared minus 2, dx by dt is 2t. So dx is 2t multiplied by dt. And I can therefore take the dx that's there still, which causes me a problem because I want x to be a variable and it's not, and I can whack that in. So integrating parametric functions is easy. You put your y equals function into the integration, and you use the x equals function to get a replacement for dx. So it gives us and I'm just putting it like that so that it's clear that I need to multiply all of this by 2t. So the y equals function just whacks straight into the integration expression. The x equals function we use to deal with this problem. That's a problem because y equals is given to us in terms of t, and we've only got, we want it in terms of x.
Why can't t be negative?
Well, okay, there's no reason why it couldn't, but we are told, remember t is a parameter, and varying that parameter gives you different values of x and y, which is how they build the function. But you've spotted that they're telling us that t is positive or greater than 0, greater than or equal to 0, because the other thing we need to do is we need to work out what values we're integrating between. We're integrating between 2 and 14. Those are x values. But we've now changed it into a t expression. So we need to actually change those x values to t values. So I also need to use this to work out the t values when x is 2. And do you see now why they said that t was positive? Because t squared is 4, so if t has to be positive, then t is 2. And then the other value, I'm desperately trying not to rub this out, is when x is 4t. So that statement there just means we're not troubled by the plus or minus thing. So we've changed the x values So I'll multiply that by brackets. Just for practice sake, finish it off. Tell me the area. Remember to use your calculator for the substitution side of it. So it's a 3-step process. Step 1, just whack the y equals equation into a function. Step 2, use the x equals function to replace the dx with something to do with dt. Step 3, if you've got limits, which are x values, change those into t values. Then you're off to the races. Remember, the place where errors most often occur in integration questions are in the substitution of values. So please use your calculator. X, 2 arrow x, and type in, obviously you haven't integrated it yet, but when you've integrated it, type in the integration and let the calculator do the substitution for you.
Why is it, how do you, what about the whole plus or minus the square root when we're working out t?
So I'm going to basically highlight these are special considerations. Is there anyone that's living and reading this right now?
You're absolutely right, that would have been a problem, and that's
You become aware of anyone that's
t is limited. And with parametrics, t is normally limited because parametric functions are often not functions that go on forever, they're often limited.
You get minus 8 for both. Minus 8 minus 1 is 0.
So minus 8 minus 8 would be 0. Have you integrated it? You'll just use that.
I've differentiated it.
So you're increasing the power, dividing by the new power.
Yeah.